Welcome to day 19 of the Advent of Code. Today continues our parsing theme. We're given a list of messages and a grammar consisting of a list of rules, and we're supposed to count the number of messages that match that grammar. Okay, and how does that grammar work? So every rule is either a single character. So for example, rule 4 would match against a string that just consists of A. And other rules are sequences of other rules. So for example, rule 0 says first you have to match rule 4, then rule 1, and then rule 5. And the other three example rules even have alternatives in them. They say you have to match 2 and then 3, or 3 and then 2. And rule 2 says first you have to match 4 and then 4 again, or you have to match 5 and 5 again, and so on. Okay, so parsing the input was again quite tedious with regular expressions. I'll show you the result here. So the simple rules are just passed into single characters. And the more complicated rules, let's take rule 1, for example, that is passed into a nested sequence of numbers, right? So the left alternative is the first inner sequence, and the right alternative is the second inner sequence, and the total thing is one sequence. Okay, and since rule 0 doesn't have any alternatives, it's just a nested sequence of numbers without, so this list doesn't have a brother basically or sister. Okay, cool. So, so the parsing already works. That's not too interesting. So maybe let's start down here. So it took me quite a long time to figure the approach out. So the basic idea was I take one input string and a rule, let's say the A rule, and then I would consume the A and return the string without the A. So that was okay for the first approach. But in part 2, that didn't work at all anymore, because there we have to explore multiple alternatives. And then at the end, I figured it's the simplest if the input and the output have the same type here. So I take a sequence of messages in, and I produce a sequence of messages. For example, if I say I want to apply the rule that accepts either an A or an A followed by a B, then this single string turns into two strings, because I could just consume the A or the A and the B. The second string simply converts into another string where the A is missing, and the third string disappears because it doesn't start with A. Okay, so it was quite hard to figure out that this was a good idea, but then it worked quite nicely. Okay, so first of all, let's see what kind of rule do we have. Do we have a single character rule, or do we have these nested sequences? So we can use the char predicate to check, is this just a single character? And if so, let's loop over all the messages in our input. And then let's say we are only interested in the cases where the rule character matches the first character of the message, right? So we could use char add message 0, good old Java interop. Okay, and if that is the case, we want to return a string where the first character is missing. Okay, so that would be a substring message starting at index 1. Okay, so that should already work. Okay, and then the more complicated rule where there's a sequence of sequences. So let's loop over the messages again, and then let's loop over all the subrules. For example, subrules could be this vector in the second iteration. And then let's compute all the leftovers, and we can do that with a reduction. Why is reduce a good idea here? Because we want to take the input messages and then feed them through rule 1, and all the survivors, basically all the ones that start with an A, are then fed through rule B. Then only the ones that also have a B after the A survive, and then we should be left with this single string in a sequence. Okay, so the collection are the subrules, and then the value, I can't just pass the message because the input is supposed to be a string. So that would be a list of message. Okay, and the reducing function, as always, takes temp and item. And let's think about what temp and item are in our case. So that would be the sub messages at the beginning, just a single message, and then the sub rule coming from those sub rules. So 1 and later 2. Okay, and then we can simply call ourselves recursively with the sub messages, apply the sub rule to our vector. So basically look ourselves up. If it's 1, we look at index 1. If it's 2, we look at index 2. And then we pass on all the rules because they are a required third parameter. They're also needed in the recursive invocation. Okay, so that should already be good. Let's see if it compiles. No, what did I do wrong? I didn't use anything. That's a classic mistake. We want to use the leftovers. Okay, so that seems to compile. Okay, so what do we do in our main code down here? So we have a Clojure map with rules and messages. Maybe let's first destructure that and say let associative destructuring on the keys. Which keys do we have? Rules and messages, as you see down there. Then we move that down. Let's put a space here. Okay, and then what do we want to do? Let's see. Let's loop over the messages again. Okay, and then let's call the consume method. Okay, so again we have to put that in a single list, and then we start with the first rule, and then we have to pass the rules. Okay, and maybe let's also combine that with a message so we understand the output better. I think that's crucial for understanding. And again, I didn't use the for, so... Oh, right, why did I put it here? It makes much more sense to put it here, right? Yeah, okay. So what does the output mean? The output means the first message could be passed successfully, so every character was consumed, and we got the empty string. The second message couldn't be matched against the rules, so nothing was returned. The third message again could be consumed. We get an empty string. The fourth message couldn't be consumed or matched. And the last message is interesting. So everything but the last character was consumed, and then the rules were finished. But we have this leftover B, right? So this is this initial substring is basically the same example as here, but this B is also here, and that's not good. We have to filter that out. Okay, so maybe let's put that here and call it leftover. Okay, so if we combine that now, how would that look? Since these two sequences are empty, they won't appear in the output. So if you loop over an empty sequence, it's like not looping over it at all. So now we should get 3 entries, the first, third, and fifth. Let's see. Yeah, and now all that's left to do is filter out this guy because the leftover isn't empty. So we're only interested in the empty leftovers, right? Yeah, and then we have 2, and then it's okay to just store the message. So those are the messages that match the grammar, and if we then count, we get 2, and that's correct. Okay, so instead of the small input, let's now use the large input. Then we get 156, that's correct, and it takes 800, 550, 570, yeah. So roughly 550 milliseconds. Again, micro benchmarking, don't trust me too much here. Okay, so how could we speed this up from 500 to 600 milliseconds? Well, first of all, here we have Java interop calls, and again, since the type of message is not known to the Clojure compiler, this will generate reflective bytecode. That's slow. But if we tell it that these are strings, then this should be significantly faster than 543 milliseconds. Let's see. Yeah, 400, 300, 300. Yeah. Somewhere around twice as fast, right? Maybe not quite. Okay, cool. So that's already quite nice. And then a second performance bottleneck is this substring operation. So in the first, I don't know, 15 years of Java, substring was a constant time operation because it just provided a subview into the original string. And then the powers that be decided it was a bad idea. If you have, a small substring into a really large string that isn't referenced anymore, that large string can't be garbage collected. Okay, so what would be an alternative? So we can also turn strings into sequences. So if we start with hello, that's of course a Java length string. But if we turn it into a sequence, then we get 5 characters in a so-called string seq. And then calling rest on that is constant time. Okay, and we can do that as many times as we want. And then later here we get empty sequences. Okay, and an alternative to rest is next. That's a little more eager. It will say instead of an empty sequence, it will return nil. Depends on your use case what you prefer here. Okay, cool. So maybe let's say no, that's not really a string. Instead, let's here say we want the first element inside the message sequence, and if it's a string, it will be turned into a string seq first. And here, what do we want here? Yeah, do we want rest or next? Maybe let's start with rest message. Okay, does this still work? Yeah, and you see it's quite a lot faster. It's maybe again a factor of 2.5 or something. So in total, maybe a factor of 5 now faster than the original. Okay, I think that's quite interesting. And again, those are micro benchmarks in part 2. It's obvious that it's really faster, but I don't want you to have to wait so long every time I test this. Okay, cool. So we made it quite fast. So what would happen if we used next instead of rest? Then we get a null pointer exception down here because you can't call isEmpty on nil, of course. No? So let's change it back to rest. Okay, cool. So for part 2, the rules change slightly. So rule 8 is replaced with these two alternatives, rule 11 with these two alternatives. And what's interesting is that we now have a recursion in our rules. So that wasn't the case before, but now rule 8 refers to itself. And the rule that refers to itself uses the other rule as a prefix. So if you're in this state in the parsing and you say, well, yes, rule 42 applies, at this point in time, you can't decide if applying rule 8 again is a good idea or not. So you have to try both ways, and that's why returning a sequence here is a good idea. Okay, and here in the second case, similar, but now the recursion is not at the end, but in the middle of the first one. Yeah, so in theory, the performance can explode, and you see that indeed happens. Okay, so let's apply those rules. Oops, part 2 rules. Yeah, and then, 156. Did I forget something else? No, that was complete nonsense. I was in the wrong spot. Here I have to apply part 2. Yeah, and then we get 363, that's correct, and 690 instead of 120. Yeah, so about now 5 times slower again. Okay, yeah, and the explosion is because of this recursion and the non-determinism. We don't know if it's a good idea to pick ourselves again or not. So we have to explore both ways. Okay, yeah, what else could we change? So when we have a variable called message and we only use it with a first and a rest call, of course we can also destructure it, right? So let's call it initial and leftover for symmetry with the other case. Then this becomes initial, this becomes leftover. And then we get our null pointer exception again, because apparently sequential destructuring gives you nil and not an empty sequence. So let's replace this with a nil predicate. Okay, and then it works again. Beautiful. Can we see that this destruction really calls next instead of rest? Well, I could press Ctrl Shift F11 for recursive macro expansion and and pretty printing. And if I scroll down 1, 2, 3, 4, 5, 6, yeah, I think here we can see it. Yeah, so you can see that the initial is initialized with first, and that leftover is initialized with next. So here's your, your proof in the macro expansion. Okay, so that makes it a bit nicer. So we have leftover in both cases. Okay, then at some point I thought, well, why are we even looping over the messages and then passing, singleton lists into the consume function? Can't we simply get rid of the outer iteration and then simply pass all the messages at once? Right? I want to know all the messages, do they pass rule 0? So this should work. Where is message? Okay. Did I do something really stupid? Oh, right, of course, here. The message isn't available anymore, so let's use the leftover. Okay, and that works, and we get the same result. Okay, so can we also do that above? That would be here. Okay, now we get a Stack Overflow error. And I researched this, and there's an interesting blog post by Stuart Sierra that says, don't mix lazy sequences with eager reductions. And I assume this is an instance of this classic pitfall, but I'm not quite sure because I just learned about it yesterday. Okay, so if you have another idea why this blows up, or if you can confirm that this is indeed the problem, then please let me know. And also if you have an alternative approach that is even simpler or much faster or takes, is just interesting because it is completely different, let me know in the comment section below.